Hello friends. So welcome to a lecture series on multivariable calculus. So today we will dealing with multiple integrals. Now we already know what integral y dx or integral x dy gives. You see, when we talk about integral y dx or integral x dy, what does it give? It gives area. You see, when you have a curve, say y equal to fx and say x is varying from a to b, and you are interested to find out suppose this area. So how you find this area? You take a strip along y axis, okay. So this is y, this is dx, so the area is y into dx, and you sum up it over all the strips. You move the strip over the entire region, you sum up it, all these small strips, and this will give integral y dx from x equals to a to x equals to b. So it basically gives area below the curve y equals to fx, above the x axis, and between line x equal to a and x equal to b. Similarly, if we talk about this integral, so this integral, for this integral curve is something like this. This is x equals to fy, where y is varying suppose from c to d, and we are talking about this area. So we take a strip parallel to x axis. This is x and this is dy. So this is x dy, and when we sum up this strip over the entire region, this will give the area of the shaded portion, which is integral, which is in single integral x dy, and x is varying from and y is varying from c to d. Okay, this is single integral. Now how can we define double integral? Okay, the double integral. So double integral over rectangles. Consider a function fxy defined on a rectangular region R, which is x varying from a to b and y is varying from c to d. So you have a rectangle now. Suppose you have a rectangle. Okay. Now to find out to define double integral of f over this rectangle, we first divide this rectangle into number of vertical and horizontal strips. Okay. Now we take a small portion, say this portion, say this is dx and this is dy, and in this small portion take a point, say xk yk. Okay. The functional value at this point is f of xk comma yk into dx dy. Now what we are having basically, we have a rectangle. Okay. We have a rectangle. Suppose this is the rectangle. Okay. We divide this rectangle into number of vertical and horizontal strips. Take a small portion of area dx dy. Take a point xk yk on that small portion. Now at that portion, at that point, f xk yk gives height. At that point, f xk yk gives height, and dx dy is that small portion. So f into dx dy will give volume of that small strip, volume of that small portion, and you sum up it over entire rectangle. Okay, you sum it up, k from 1 to n, say n number of strips, and then take limit n tends to infinity. That means limit n tends to infinity means you are taking that strip smaller and smaller. So this will converge to, this will give double integral over rectangle R of f x y into dA. dA may be dx dy or dy dx. So this will be the double integral f x y dx dy or dy dx. So what does it give basically? It gives volume of the solid over the region R, and height is governed by z is equals to fxy. Region is R, Here we have defined region as rectangle, region may be anything, region may be square, region may be some other portion, okay, on xy plane, okay, region may be anything. Now this gives volume of a solid which is obtained over the region R, and height is governed by z equal to fxy, okay. Now if fxy is 1, now this double integral over R dA, this basically gives area of the region R. Okay. So area of a region can be computed by single integral y dx or x dy, or can be computed by double integral also, that is double integral over R dx dy or dy dx. Suppose these are two curves, say it is y square equal to x and say it is x square equal to y, and you want to find out the area enclosed by these two curves. What is that area enclosed by these two curves? Is this area. Point of intersection is clearly 1, 1. 1 satisfy this, 1 satisfy this, okay. Now you want to find out the shaded region R. So we can compute this shaded region. So area of the shaded region will be double integral. We can take dx dy or dy dx. Suppose we are taking dx dy. Now in dx dy, if you are taking dx dy, so take a strip parallel to x axis first. So you take a strip parallel to x axis, Now what is x here? Lower bound, and this is upper bound of x. What is x here? X here is this curve, that is y square. And what is x here? X here is under root y. And y is varying from which point to which point? You see, y is varying from 0 to 1. In the entire region, y is only between 0 to 1. So y is varying from 0 to 1. So this is how we can obtain the area of shaded region by double integral. Now you can simply solve this integral. How can we solve this? It is 0 to 1. Now first you integrate respect to x, keeping y constant. Integral of dx will be x. This is y square, this is under root y dy, okay. Now upper limit minus lower limit, this give integral 0 to 1, this is under root y minus y square, upper limit minus lower limit into dy. Now you integrate over y. So integration of y raised to power 1 by 2 is y raised to power 3 by 2 upon 3 by 2 minus y cube upon 3, and it is 0 to 1. So when y is 1, it is 2 by 3 minus 1 by 3, okay. At 0 it is 0, so it is 1 by 3 square units. So this will be the required area of the shaded portion. Now this area can also be find out if instead of taking dx dy, we take dy dx, okay. Suppose we take dy dx. So area of shaded region is equal to double integral. Suppose we take dy dx. Now if you are taking dy first, so take a strip parallel to y axis. So instead of taking a strip parallel to x axis, take a strip parallel to y axis. Now if you take a strip parallel to y axis, what is y here? Y here is x square, okay. And what is y here? Y here is under root x, and x is varying from this point to this point. The minimum value of x is 0, maximum value of x is 1. In this region, x is always varying between 0 and 1 only. So 0 to 1. So this will be equal to 0 to 1, and the integration, first you integrate with respect to y, keeping x constant. This is equals to 0 to 1, upper limit minus lower limit. So, this is x raised to power 3 by 2 whole raised to upon 3 by 2 minus x cube by 3 from 0 to 1. So, we get the same answer, which is 1 by 3 square units. Okay. So, that is how we can find out the value of the area of the shaded region using double integral. Okay. Now, suppose you have this type of problem. You have a circle, say x square plus y square equal to 1. You have a parabola, say y square equal to x. Okay. Now, you are interested to find out this shaded area. So, how can you find this? Now, suppose this point is alpha beta. This point can easily find out by finding the point of intersection of these two curves. Okay. Say this point of intersection is alpha comma beta. Now, we are interested to find out the area of the shaded portion. So, how can you find out? So, area of shaded portion or shaded region will be equals to double integral. Suppose we take dx dy. So, dx is first. So, take a strip parallel to x axis. So, you take a strip parallel to x axis. What is x here? X here is y square. And what is x here? X here is under root 1 minus y square. And y is varying from which point to which point? Here y is 0 and here y is beta. So, y is varying from 0 to beta. So, this will be the representation of area of the shaded region. Now, this area can also you find out if instead of taking dx dy we take dy dx. Okay. So, this suppose this is R. So, same R which is the area of this region can also find like this, you see dy dx. So, you have to take a strip parallel to y axis. If you take a strip parallel to y axis here, okay. Now, if you take a strip parallel to y axis here, so here the lower bound is y equal to 0 and upper bound is this. However, if you take the same strip over here, the lower bound is y equal to 0 and the upper bound is on the circle. That means, when we move this strip on the shaded region, the lower and the upper limits are changing. So, we have to split the region. From this intersection point, if you draw a line perpendicular to x axis from here to here, from O to P, you have to divide this region into two. The first region is this, where y is varying from 0 to this point. Here y is, for this curve, y is under root x, and x is varying from this point to this point. This point is alpha 0, from 0 to alpha. And in this region, when you take a strip parallel to y axis, here y is 0 and here y is on the circle, which is given by under root 1 minus x square, and x is varying from alpha to 1, because here is alpha, x is alpha and here x is 1. Okay. So, the sum of these two will give area of the shaded region. So, whenever you take a strip either parallel to x axis or parallel to y axis, you move that strip in the entire region. If the lower and the upper bound of the region is not changing, so we do not need to split the region. If it is changing, then we have to split the region. In the same, if we take a strip parallel to x axis for this portion, if we move this strip in the region, the lower and the upper curve are not changing. So, there is no need to split the region. However, if we take a strip parallel to y axis and move this strip in the region, move this strip in the region. So, here lower and upper curve, lower is a x axis, upper curve is a parabola. Here it is an x axis and upper curve is a circle. So, it is changing. So, we have to split the region. Okay. So, that is how we can find out area of a region using double integral. So, now we can solve these problems also. Say the first problem. The first problem is double integral 0 to 3, 0 to 2, it is 4 minus y square dy dx. Now what basically this is? This is volume of a solid erected on a rectangle, where y is varying from 0 to 2 and x is varying from 0 to 3 and height is governed by 4 minus y square. You have a rectangle on xy plane where x is varying from 0 to 3 and y is varying from 0 to 2, we have a rectangle, and height is governed by, for every xy in that rectangle we have a corresponding height which is governed by 4 minus y square, and 4 minus y square into dx dy or dy dx will give the volume of the solid which is erected on that rectangle. So, this is basically volume of a solid on the region this, and the height is governed by this expression. So, how to evaluate this? So, this is limits for y, this limits for x. So, this is 0 to 3. You simply integrate this keeping x constant. So, it is 4 y minus y cube 0 to 2 dx. It is 0 to 3, it is 8, it is 4y minus y cube by 3, okay. Then it is 8 minus 8 by 3 dx, and it is equals to 8 minus 8 by 3, integral of dx is x from 0 to 3, which is 8 minus 8 by 3 into 3 minus 0, which is 24 minus 8 equal to 16. So, that will be the value of this expression. Okay. Now, similarly, if you want to solve the second problem or the next problem, that also can you find out. It is integral pi to 2 pi, integral, it is 0 to pi sin x plus it is cos y and dx dy. So, these are the limits for x because dx is coming first, and these are the limits for y. So, y is from pi to 2 pi. Now, you integrate respect to x keeping y constant. So, integral of sin x is minus cos x plus integral of this is x cos y, and x is varying from 0 to pi dy. So, this is equals to pi to 2 pi. Now, you substitute x equal to pi, okay. It is minus 1, upper limit minus lower limit minus 1, then cos y comes out because we are taking y as constant, these are limits for x. You take x equal to pi and then x equal to 0. Okay, and this is dy. Now, this is integral pi to 2 pi, this is 2 plus pi cos y into dy. Okay. Now, this will be 2y plus pi sin y from pi to 2 pi. This is equals to pi 2 pi minus pi, upper limit minus lower limit, and pi 0 minus 0. So, this is simply 2 pi. So, that is how we can find out the values of these double integrals. Now, the Fubini first form, what is that? If fxy is continuous throughout the rectangular region R, which is where x is varying from a to b and y is varying from c to d, then if you interchange the limits, then the value will remain the same. So, if limits are constant, so and we interchange the limits, so the value of the double integral will not change, will not affect it. Okay. This is Fubini's theorem, or the first form. Now, the stronger form of Fubini is, let f(x,y) be continuous on the region R. If R is defined by x varying from a to b and y is varying from g1x to g2x, which g1 and g2 are continuous on closed interval a to b, then double integral over R f(x,y) dA will be given by, now here y is varying from g1 to g2. So, you take the limit of y g1 to g2 and x is varying from a to b, f(x,y) and then dy dx, because first you are putting the limits for y and then for x. So, here will be dy dx. Similarly, the another form of this is, if we defined R as y is varying from c to d and x is varying from h1y to h2y, with h1 and h2 continuous on closed interval a to b, then double integral over R f(x,y) dA will be given as, now you first integrate with respect to x, taking the limits of x from h1 to h2 and then y from c1 to c to d, and take dx dy, because you are putting the values of limits for x first. Now, suppose you want to solve these problems. So, we can take the first problem. The first problem is double integral. Now, here it is 0 to x and then 0 to 1 dx dy dx. So, these are limits for y and these are limits for x. Of course, because y is first, so these are limits for y and these are limits for x. So, how can you find this integral? So, this is integral 0 to 1. You first integrate this with respect to y, keeping x constant. So, it is x into y square by 2 and y is varying from 0 to x and dx. So, 1 by 2 can come out, integral 0 to 1, it is x into x square dx, okay, because for 0 it is 0, is equals to 1 by 2 integral 0 to 1 x cube dx, which is equals to 1 by 2 x raised to power 4 by 4 0 to 1, which is 1 by 8. Okay. Now, what this represent basically, let us see. Now, this here y is 0, here y is equal to x, here x equal to 0 and x equal to 1, x equal to 1 means this line. Okay. So, which region you are having? So, you take a strip parallel to y axis, dy is there, you take a strip parallel to y axis, here y is 0 and here y is x and x is varying from 0 to 1. So, this is the region. Okay. Because in order to check whether this is this triangle or the above triangle, you take a strip parallel to y axis, because dy is there first, you take a strip parallel to y axis. Now, here y is 0 and here y is x. So, here y is 0 to x and x is varying from 0 to 1. Okay. So, this shaded region is this region R. So, what we are having basically, we are having a triangle which is given by this shaded region on the xy plane and a height is governed by z equal to xy. Okay. And the solid directed over this and the volume of solid directed over this is 1 by 8. Now, similarly, you can solve these problems. Suppose you want to solve the last problem. Okay. Similarly, you can solve second and 3. The last problem, let us suppose it is integral 0 to 1 to ln 8 integral 0 to ln y e raised to power minus x square minus e raised to power x plus y, sorry, and it is dx dy. So, these for x, these for y. So, again you can integrate in the same way. it is e raised to power x into e raised to power y. When you integrate respect to y, it will be e raised to power x will remain as it is, and e raised to power y will remain as it is. Integral of e raised to power x will be e raised to power x, and it is 0 to ln y dy. So, this is equals to 1 to ln 8. Now, when x is ln y, so it is y, and at 0 it is 1, and it is e raised to power y dy. Now, you can simply integrate this using product rule. So, it is first as it is, then it is e raised to power y minus derivative of this is 1, integral of this is y. So, this is 1 to e raised to ln 8, okay. And then you can simply substitute upper limit minus lower limit. At y equal to 1 it is 0, at y equal to 1 it is e. So, this will be the value of this double integral. So, these are some of the properties of double integral. Now, triple integral. Now suppose we have a solid, okay. Now, if we have a solid, say we have a cuboid. So, we divide this along x axis, along y axis and along z axis. We divide that solid along x axis, y axis and z axis, and take a small solid of volume delta x, delta y, delta z, and pick a point, say xk, yk, zk in that point, and the value of the function that point will be f xk, yk, zk. Then we take the sum of this, which is f at xk, yk, zk, delta x, delta y, delta z, and k varying from 1 to n, and limit n tending to infinity, means we are taking the solid smaller and smaller, very close to 0, I mean very small solid. Then this will be triple integral over volume V of f dv. Okay. So, this is how we can define triple integrals. Now, suppose you want to solve the first problem. Okay. This is triple integral 0 to 1, 0 to 1, 0 to 1, x square plus y square plus z square. First we have dz, then dy, then dx. This means this is for z, because dz is the first one, then it is y, and then it is x. So, first you integrate with respect to z, keeping all other variables constant. So, this will be double integral 0 to 1, 0 to 1, integrate with respect to z, keeping other variable constant. So, x square z plus y square z plus z cube by 3, and z is varying from 0 to 1 dy dx. So, this is equals to 0 to 1, 0 to 1. So, it is x square plus y square plus 1 by 3. When you take z equal to 0, all are 0. So, it is dy dx. Now, you integrate with respect to y, keeping other variable constant, other variable is x, keeping that constant. So, it is 0 to 1, it is x square y plus it is y cube by 3 plus, and 1 by 3 is y by 3 from y equal to 0 to 1 and dx. So, this value will be, it is 0 to 1, you put y equal to 1, then it is x square plus 1 by 3 plus 1 by 3, and for y equal to 0, all are 0 into dx. So, this is again equal to, now it is x cube by 3 plus 2 by 3 x from 0 to 1. So, it is 1 by 3 plus 2 by 3, which is 1. So, the final answer is 1. So, in this way you can solve such type of problems, and similarly you can also solve the next problem of this slide. Okay. These are some of the properties of triple integral, like you can take constant out, if we have a addition or subtraction of two triple integrals, it can be write separately. And if f x y z is greater than or equal to 0 on D, then the triple integral of f x y z into dv is also greater than or equal to 0. And similarly, if f x y z is greater than or equal to g x y z, then the corresponding triple integral of f will be greater than or equal to triple integral of g. Okay. Now, if f is 1, you see, if we are talking about triple integral over d of dv. So, what this give? This give volume of solid D. This gives volume of the solid D. Okay. So, thank you very much.